In this video, we're going to set up the expert elicitation that we'll be talking about during this module in the course. We're going to begin with the Glmris report. You've been hearing about that as one of our case studies for the course, and I'm beginning with the risk assessment here in Appendix C. So I'm going to fast forward here to page 28, and page 28 is going to review the probability of establishment. Now you know that risk is a consequence times a probability, but in this particular case we're going to focus primarily on the probability of establishment of aquatic nuisance species, specifically the Asian carp. The model that we used is seen here. The probability of establishment is defined as the product of these five probabilities. The probability that there is a pathway times the probability that the aquatic nuisance species arrives at the pathway times the probability that the aquatic nuisance species passes through the pathway times the probability that it colonizes once it reaches the other side of the pathway times the probability that it spreads from that colony. This was the qualitative risk assessment, and we thought it would be the easiest thing in the world to make this quantitative at some point. And now let's switch over to Google Earth here and take a look at Dresden Island Lock and Dam. This is on the Illinois River downstream of Chicago. Asian carp have already made their way through this lock and dam, and they now occupy this Dresden pool, the area upstream of the Dresden Island Lock and Dam. So you can see this area here already has aquatic nuisance species, specifically Asian carp, in it. As a result of the previous Glmris risk assessment, the U.S. Army Corps of Engineers was directed to try to prevent passage of the Asian carp upstream at this point here, Brandon Road Lock and Dam. One of the reasons this area was chosen is because there is no evidence that Asian carp have made it above the Brandon Road Lock and Dam. So there is no evidence they are in the Brandon Road pool at the current time. This dam that you're looking at here has well over a 20-foot rise. So it is unlikely that fish will make it into the river upstream of the lock and dam by going through the dam. This little canal over here is permanently sealed at this point here. The canal that goes off here is not hydrologically connected to the upstream, and so it would be most likely through the lock that aquatic nuisance species, specifically Asian carp, would move upstream, and the Corps has been directed to try to prevent this at just this location. So you've seen the model. Our pathway begins here, and we are trying to prevent passage up this aquatic pathway and then via one of the several other aquatic pathways that exist and into Lake Michigan. As I mentioned, this seemed to be the easiest thing in the world. We have a very simple model. We just get 5 numbers and multiply them together. But when we began to think about the specifics of how this would be done, we ran into 2 problems, specifically with these components right here. Estimating the probability that a pathway exists is easy. We were just looking at the pathway. We know that probability is 1. The probability that they arrive meaning that Asian carp arrive at Brandon Roads, was a little bit trickier, because when we say that aquatic nuisance species arrive, then you immediately get into questions of, well, in what numbers? In very large numbers? Small population? Medium population? A large population? What size population are we talking about in that Dresden pool? So any of the area downstream of Brandon Road is considered the Dresden pool. And we realized that to handle this arrival, we might have to address different sized populations, an idea we hadn't quite considered. And then when we came to the passage, the idea of Asian carp passing through this pathway from Brandon Road all the way up to Lake Michigan. So there are water quality issues. There is an electronic barrier at Romeoville. There are some substantial barriers at Brandon Road Lock and Dam. And then we realized that would be a very difficult question to ask. Excuse me. Does the passage of one fish constitute passage? Does the passage of a million fish constitute passage? And it makes a difference. Are we talking about big fish or small fish? Fish of sexual maturity? Same species, different species? There were a lot of different issues that arose over the idea of passage, and it became difficult to imagine how an expert could give one probability of passage when there were so many scenarios. If they ask, do we consider the passage of a single fish? How do we answer that? Do we say yes or no? Because we want passage to remain independent of these other quantities, including the probability of colonization. So we realized there was a problem with probability of passage. We were going to have to define that somehow. And in a similar fashion, particularly because we were concerned with numbers of fish for passage, we ran into issues about colonization. Would there be colonization? Given that there is passage, what's the probability of colonization? Well, one of the things that you would need to be able to say is how many fish have passed. If we are going to give the expert the condition that there has been the passage of fish, we need to tell them how many fish. If it's one fish that's small, there's not going to be any colonization. If there are a million fish that are large that enter together, there will be colonization, and there are countless permutations in between these two. So what we ran into early on was the realization that it wasn't going to be as simple as getting 5 probability values and multiplying them together.